We thank Paulo Bartolo for accepting our invitation, and we will request Professor Amaresh Chakravarti to introduce CFC and Professor Paulo Bartolo to the audience. Thank you very much.
Thank you, Dr. Srinivas. Much appreciate. So I would like to start by first, extending my warm welcome to everyone who has joined and those who are still joining to this webinar series. I think we have probably already covered more than 20 presentations in this webinar series, and for those who are joining for the first time, this is a joint webinar between the Center for Product Design and Manufacturing at Indian Institute of Science and the Common Engineering Facilities Center, which is a center of excellence under the Department of Heavy Industries, Ministry of Industry, Indian government that are driving the Smart Factory initiative at IISc. So the webinar series is on advanced design and manufacturing. So we have speakers from both, and the goal of this Smart Factory initiative is to champion all causes related to Industry 4.0. And as Dr. Srinivas says, this is also a celebration of India's independence. This is the 75th year of independence of India. And there is nobody I can think of who is better than Professor Paulo Bartolo for celebrating this particular webinar series for multiple reasons. I mean, if you look at the bigger background, the Manchester played a critical role in the lead up to independence of India, because that's where a majority of the textile industry of Britain was situated, which was a major sort of point in the turning of history that was linked, I think, inextricably to India's independence. The second reason, of course, is the fact that Professor Paulo is actually the Industry 4.0 lead at the University of Manchester, and one of the most distinguished professors in manufacturing in the UK. So it's an absolute pleasure and an honor to welcome him here, and I'm absolutely delighted that he's able to find time in his incredibly busy schedule to join us today. And so I would just like to briefly introduce Professor Paulo Bartolo. He's a chair professor, of course, on advanced manufacturing at University of Manchester. And as I said, he's the Industry 4.0 academic lead. He's also the head of the manufacturing group, member of the Department of Mechanical, Aerospace and Civil Engineering Executive Committee, member of the Advanced Manufacturing Strategic Oversight Committee, theme leader of Industry 5.0 Societal Challenge Area within the Digital Futures, and member of the Management Board of the EPSRC, that's the Engineering and Physical Sciences Research Council, and the MRC, Medical Research Council Centre for Doctoral Training in Regenerative Medicine. He has a PhD in Polymer Physics from the University of Reading in the UK, and an MSc and a first degree in Mechanical Engineering from the University of Lisbon, or Lisboa probably, in Portugal. Professor Paulo has authored, of course, a very substantial number of publications, over 600 in journals, book chapters, and conference proceedings, and has been a co-editor for 22 books and has 16 patents to his name. And if I may add to that, he's also the chair for the Matador Conference, which is a well-known conference in manufacturing, running for many years, and it's intended to be held this year at University of Manchester. So without further ado, I'll just leave the virtual podium to Professor Paulo. One day I hope he will be here at IISc holding a physical podium. And his talk is on mass personalization strategies to additive manufacturing. And over to you, Professor Paulo.
Thank you very much, Professor Amresh, for your kind introduction, and thank you very much for the invitation to deliver this seminar. It is not only a great pleasure, but it's also an honor to participate in this seminar series. As you know, I'm coming from Manchester, and if you don't know where is Manchester, so Manchester is located at the center of the UK. in between London and Edinburgh. And it's in a lovely region. So not far from Manchester, 1 hour by car, we have the Lake District, and also more or less 1 hour by car on the opposite direction, we have the Peak District. So the surroundings are quite beautiful. If you like football, Manchester is also the best place to be. So we have two very strong teams, Manchester United, Manchester City. Manchester is a city of sports. And of course, it's the home of the University of Manchester, a strong university. We have the largest university single campus in the UK, quite close to the city centre. As Professor Amrut mentioned, I have multiple roles at University of Manchester. One is to be the academic lead for Industry 4.0. And this means that I need to interact and to push colleagues from our three different faculties to work together in the area of Industry 4.0. And for us, Industry 4.0 is more than technology. It's also about people. And that's why we usually define Industry 4.0 as a complex social and technical transformation of the world. So people are always present in our Industry 4.0 vision. Of course, that from a technological perspective, Industry 4.0 is for us about the use of digital tools and technologies, advanced materials, big data and automation for sustainable and smart factories, services and products. I'm also the head of the manufacturing group. So this is a group of academics. We have a total of 4 chair professors and several readers, senior lecturers and lectures. We are responsible for 2 master programs, one program in engineering design and another one in advanced manufacturing and system management. And in terms of research, the group is focusing on 3 main domains: innovative manufacturing process, smart manufacturing, and digital manufacturing. All of these domains enabled by key technologies, and these key technologies for us are laser-based process, additive manufacturing, multi-scale manufacturing, mechatronics, and virtualization tools. And in our research, we are trying to address key economic, social, and environmental challenges. So an important area of research in the group is related to intelligent manufacturing, and we are doing it through a wide range of techniques, not only additive manufacturing, but also hybrid systems, automation. We have a group of colleagues focusing on human machine and machine collaboration, also on smart inspection and predictive maintenance. We are also doing research in terms of sustainable manufacturing and on human-centric manufacturing and human-centric design. We have strong links with the Thomas Aston Institute in Manchester, where our work is essentially around the concept of human-centric manufacturing and safety and health in the working environment. So regarding to intelligent manufacturing or smart manufacturing, this is basically the generic methodology that we are adopting for different industrial sectors. So our approach is focusing on 3 generic pillars. Of course, the first pillar is about data. We call it as data-driven intelligence, where we are using cloud computing, Internet of Things, artificial intelligence, and big data to collect the necessary data for the smart manufacturing domain, where we are not only looking into the part or to the design issues related to the part, or the fabrication processes to create the part. We are also looking to the workforce at the company, to the customers and to the suppliers, And finally, the third pillar, which is the impact related to the implementation of smart manufacturing strategies, where our goals is to minimize energy consumption, raw materials, improving safety, efficiency, productivity, accelerate time to market, and improving quality. We are particularly interested in, and we are doing this with several companies, is to optimize production, looking to the shop floor. And to do that, we are developing digital twin programs, and the generic representation is illustrated here. So basically, we are using this shop floor digital twin to provide an additional tool for companies to support their decision making. Besides being head of the manufacturing group, I'm also leading a research group focusing on not only additive manufacturing, is essential additive manufacturing, but also hybrid technologies and advanced materials, and also modeling and simulation for multiple areas. So mainly healthcare, but we are also doing research in terms of construction, agriculture, and more recently on textiles. And today I'm going to give you some examples of our activities in all of these areas. So what is common in all of my roles is, in fact, additive manufacturing. Additive manufacturing is always present, and as you know, additive manufacturing is an enabling technology for Industry 4.0 for multiple reasons. So the potential to simplify the supply chain, the impact that additive manufacturing has in terms of reduced time to market, improve efficiency and productivity, reduce inventory, and reduce also cost of quality, make additive manufacturing a key element of any Industry 4.0 strategy. We like to describe additive manufacturing as a platform for material design to create new things. And at University of Manchester, we have a wide range of commercial available machines, but we are also developing our own machines, trying to address some limitations of existing machines or developing machines for specific applications. An example is illustrated on the right side of this slide. So this is an hybrid machine that we developed. So the machine comprises 3 printing heads. So this is from an additive manufacturing perspective, an extrusion-based machine. So comprises 3 printing heads, 2 pressure-assisted and 1 screw-assisted printing head, plus a multi-plasma jet system. And with this machine, we can print up to 3 different materials per layer, but we can also use the plasma jet system to do surface modification, surface coating in a selective way. So we are using this machine to create functional graded structures. We are using this machine to modify the wettability of our printed materials, creating, for example, self-cleaning structures. We are also developing new printing heads using screw or pressure-assisted printing heads with multiple material reservoirs, again to create multi-material fibers or functional graded fibers. And we are also developing coaxial printing heads to create core shell fibers. The most recent developed is illustrated on the left side and corresponds to this coaxial printing head with an expanding chamber nozzle, which allows us to print better defined core shell fibers. This is an example of a machine that we developed in partnership with colleagues at Sabancı University. This is a machine that allows to print multi-material filaments The key issue here is to control the rheology of the material. So we need to guarantee a good printability, but we need also to guarantee that the different materials don't mix in the printing head or after being printed. So we have, as many other groups, a wide range of gantry systems. We are also developing robotic-assisted additive manufacturing machines. I'm going to show you one or two examples later. But right now we are focusing on mobile robots, and we are developing a platform where we are using multiple mobile robots working together in a collaborative way. And this is an example of one of the prototypes that we are developing. Of course, as I mentioned, if additive manufacturing is a platform to design materials or for material design, naturally that we are interested in creating smart structures, and we are doing this by processing smart materials. So not only materials that can change their shape according to specific environmental conditions or changes in the environmental conditions, but also materials, especially inks, that can change their color, for example, if we change, again, environmental conditions. So, for example, light or temperature. To process shape memory metallic alloys, we develop an electrochemical additive manufacturing machine to create smart structures based on the use of shape memory polymers. So we are used standard extrusion machines. This was one of the first machines that I developed and my group developed a few years ago. I was in Portugal at the Polytechnic Institute of Leiria when we developed this machine, which was the consequence of my PhD. So this is a multi-material stereothermal lithography machine. Contrary to a standard stereolithography, we are not using lasers, so we decided to use a low-cost Mercury lamp. And then we use different filters to split light into different wavelengths. And essentially, the machine operates with two different wavelengths. One is UV radiation, and the other one corresponds to near-infrared radiation. And then we use optical fibers to irradiate a digital micromirror device shown here. In fact, the machine has two DMDs. This image only shows one DMD. And then the image created in the DMD is transferred and projected on the VAT through a reduction lens. So this lens reduces the image created on the DMD 10 times. So if we consider that each small mirror of the DMD as 40 micrometers per 40 micrometers, we can create an image on the surface of the resin of 1.4 per or 1.4 micrometers of size. We develop also a carousel of VAT, so these allow us to create multi-material structures using this technology. And we use also this technology to create metallic parts. In fact, I believe that my group was the first group in the world to propose the concept of metallic stereolithography using this system. And of course, that we are also developing apps to transform additive manufacturing into IoT devices, allowing remote users to monitoring the fabrication process, to evaluate the performance of the system, but also to monitor material supply. But additive manufacturing offers a wide range of advantages, and some I mentioned before. But due to the unique characteristics of additive manufacturing, it is now possible to combine additive manufacturing with topology optimization, allowing us to create lightweight structures or to redesign existing parts, reducing their weight without compromising mechanical performance. We are exploring this in multiple areas. I selected one example related to medical applications. So, as you know, most of the bone plates are made in stainless steel or titanium alloys. Some can be chromium cobalt. But the major issue is that the mechanical properties of these plates are quite high compared to the mechanical properties of bone. And as a consequence, we have a problem called stress shielding. So we observe after a certain period of time that there is some bone loss in the vicinity of the implant. So we decided to use topology optimization to redesign these plates, considering different physiological loads and also different values of volume reduction. And we managed to achieve a couple of designs where the plates present mechanical properties in the range of cortical bone. Those plates were made in titanium 64. We use both electron beam melting and selective laser melting to produce those plates. And then we investigate the mechanical performance of those plates, comparing them with commercial available plates like synthesis from Dupuis or Biomed. And we perform also some biological studies showing that our plates present a much better biological behavior than commercial available plates, suggesting that our plates will create a better link with the surrounding tissues. So we are now organizing everything to start some preclinical tests in animals, in chips, to test these plates. Well, one of the problems that we have in additive manufacturing is, as you know, related to the anisotropy. And anisotropy in additive manufacturing is due, first of all, to the fabrication strategy, because usually we create parts layer by layer, but it is also related to the phase change transformation that the material suffers during the printing process. The material is in the solid state, we heat the material, and then we cool the material again. So due to this morphological transformation of the material, it is difficult to control, for example, crystal orientation, crystal size, and crystal growth. In the group, we have a colleague focusing on designing the anisotropy by changing the fabrication strategy, and he is doing this using new lay-down patterns, path plane strategies, together with a robotic-assisted additive manufacturing. I'm more focusing on the phase change transformation of the material. And 3 years ago, we ran a couple of tests and we published several papers. I believe that we were the first group in the world investigating the morphological development, in situ morphological development, using synchrotron. And we are developing mathematical models now, allowing us to correlate processing conditions with the morphological development. So the impact of these processing conditions in terms of nucleation, crystallization, crystal size, and crystal orientation. And of course, the correlation of these morphological changes and the final properties of our part, allowing us to, by changing the processing conditions, to design the anisotropy of our printed parts. Of course, that Industry 4.0 is about digitization, and of course, that is also important to digitize production process like additive manufacturing. And the group is doing that. So we have colleagues, my colleague Mike Smith and John Francis. They are developing digital twins for direct energy deposition. I'm more focusing on vat photopolymerization and extrusion process. We are also starting the process of developing digital twins for laser powder bed fusion process. But so far, the digital twins for additive manufacturing are focusing on the fabrication process itself. So we are developing new strategies to enlarge the complexity of these digital twins, incorporating things related to the design of the parts and also inspection and evaluation. And of course, this requires new data analytics and also artificial intelligence engines to support any decision making to optimize the additive manufacturing process. Well, another important aspect of additive manufacturing is that additive manufacturing enables new fabrication, a totally new fabrication paradigm. So through additive manufacturing, it is possible to produce close to the point of use. And additive manufacturing is also able, as a technology, not only to reduce the time to market, but to allow companies to respond faster to the customer demands. What we are interested in about additive manufacturing is the potential of additive manufacturing for mass personalization. So no longer focusing on mass customization, but the next step, mass personalization. And the next part of my talk, it will be about the concept of mass personalization, and I will provide several examples related to the use of additive manufacturing for mass personalization applications. Through additive manufacturing, it is possible to change the role of the customers. So it's more than mass personalization. So it's not only a question of a company to produce an individualized product for a client, for a customer, but additive manufacturing allows now the customer to be also the creator. So the customer, the user, will no longer be a passive recipient in the product development process. They will create, or they will be able to create their own products, and this corresponds to a totally new fabrication paradigm. And I'm going, as I mentioned, to focus this on one or two particular industrial sectors where we are developing tools to promote this and to increment the co-creation mechanisms. There are several companies in the world exploring this. So one example is UPS, which is a Proto Labs company. Shapeways is another example. So basically, these companies, I usually describe them as Uber companies for 3D printed parts. So basically, if the user wants to create a part, but if they don't have any machine to reproduce his idea or their idea, they can send the parts, they can upload the parts, and the company will produce the parts and ship the parts to the user. In the case of UPS, they have a network of small companies or offices across the world that produce the parts close to the user. which in this case is also the designer of the product. Society is now more aware about the advantages of additive manufacturing than before. I have no doubts, because due to COVID-19 and the information about the potential of additive manufacturing to produce a wide range of protective devices, addressing the demands of hospitals, society is aware now of some of the potentials of additive manufacturing. These are some examples of protective devices that we built in Manchester during the pandemic. I'm pretty sure that lots of universities across the world have done similar work. What was very interesting during this period was to observe very nice personalized products also emerging, and I selected two. One, which is on the top of this slide, is an helmet designed by a group of designers in China. And basically, they create this Voronoi lattice structure to improve the mechanical performance of the helmet. So the impact loads are better distributed using this Voronoi concept helmet. The second one, which is on the bottom of this slide, is an helmet for sports applications, American football, and this was developed by Impressio, which again combines a lattice structure, not possible to be produced using standard technologies, plus some energy-absorbing pillars, which were made in an elastomeric liquid crystal, and again improving the energy absorption of the helmet. So, two nice examples of the use of additive manufacturing to create personalized personal protective equipment. But there are many other examples related to the use of additive manufacturing for mass personalization. One nice example is from a company in Sweden, Gaslink, which uses very complex designs. The users are able to create these designs using Gaslink software. And then these designs are used to create 3D printing lighting. Or the work from a designer, Earl Stewart, which is using additive manufacturing to create personalized shoes. Or finally, the work of a colleague and friend from New Zealand, Olaf Diggle, who is using additive manufacturing to print guitars. So nice examples of the use of additive manufacturing for mass personalizations. Companies are also aware of this, and a good example is from Barilla, which is developing machines or using additive manufacturing to allow customers to design their own pasta. So it's a normal extrusion machine. The difference is the material used by the machine. It is difficult now to travel, but next time, if you had the opportunity to visit the UK, Yeah, I leave this suggestion. There is a restaurant. It was open before the pandemic situation in London. The Food Inks 3D printing, and it's a restaurant that they don't only use additive manufacturing to print food. They use also augmented reality to provide a new environment in terms of restaurant, and everything is 3D printing. The chairs are 3D printing, the forks are 3D printing, so everything is 3D printing in this restaurant. Well, as I mentioned, in the group, we are using additive manufacturing and advanced materials for several industrial sectors, and the focus is always to develop mass personalization strategies within these sectors. One of the sector that I would like to bring today is related to construction. In 2019, we published the first paper where we described the concept of construction 4.0 and the key elements of a construction 4.0 environment, which it's similar to the concept of Industry 4.0 for manufacturing, and the aims are the same. So it's to promote the communication between the different stakeholders, is to maximize productivity and efficiency, reducing waste, and increase sustainability. So this is the figure, a generic representation of our concept of construction 4.0. You can find it this concept in the paper that we publish in Automation in Construction journal. In terms of additive manufacturing, we are developing several things. So we had a project, an EPSRC project called Rebuild, where one of the aims was to reuse part of the material resulting from building demolish for additive manufacturing and to create new construction elements. This is particularly critical in the UK because every year we have more than 50,000 buildings being demolished, which generates more than 400 million tons of waste material. So one of the focus was to reuse part of these material. In parallel, we are also trying to develop new printing strategies to combine multiple materials, reducing the amount of concrete, and by doing this, reducing the environmental impact of construction. So we started as other groups printing concrete using robotic assisted machines, and later we started a project with a Portuguese company supplying cork. And we modified our printing system. We built a new printing head with a new mixing chamber. And basically, the idea was to print mixtures of concrete and cork. We developed a software, and the aim was to replace concrete by mixtures of concrete and cork in areas where the construction element was not highly loaded or under significant loads. So as I mentioned, we developed a new printing head to do that. We developed this software, and this is a simple example. We started with a building element with a metallic pillar, and all the building element was made in concrete. And then we used the software to redesign this building element. And the result is illustrated here. So basically, in areas less loaded, it was possible to replace concrete by a mixture of concrete with 29% of cork. We can go to high levels of cork. The limitation here was essentially the motors that we used. So it is necessary to use more powerful motors to print mixtures with high levels of cork due to the rheological properties of the mixture. This is one of the first examples of the printed structure. So we started in one side printing concrete and 30% of cork, and gradually the composition changed, and at the end we finalized by printing only concrete. So as you can see, some problems, some cracks, some pores due to the lack of process optimization. So we spent some time optimizing the process, and this is another example of a structure, again with a gradient of cork. And by doing this, we cannot not only reduce the amount of concrete, and these images show that we have a very good control over the printing process and the mixture composition. But the use of concrete and cork allows also to improve the thermal performance of the construction element. So this is a scanning electron microscopy image showing some cork elements embedded in the concrete matrix. So as I mentioned, one of the key advantages of using this strategy is to improve the thermal efficiency of the construction elements. We demonstrate that using modeling and simulation. So we consider that the energy consumption required to keep the temperature of a room with a temperature ranging between 18 degrees and 26 degrees throughout the year. And we simulated this considering two cities, one Lisbon in Portugal and the other one in Manchester. And as you can see, when we move from a traditional wall made in concrete to walls with a gradient structure, maximum of 30% of cork, it was possible to achieve a 14% of reduction in terms of energy consumption. So besides the sustainability issues, this approach allows us also to reduce energy consumption. Well, another area where mass personalization is critical is related to the medical sector. Here besides of course different types of medical devices, we are focusing on building repair approaches. So we are not building body spare parts, but we are developing strategies to treat some diseases or health problems. We are exploring two main strategies as illustrated here. So in one case, we are using additive manufacturing to create these porous structures, which we call scaffolds. But for a mechanical engineering, the best definition of a scaffold is a biomold. So if we need to create, to produce plastic bottles, we need to have an injection mold, and this injection mold will give shape to the molten plastic. This is the same. So we use additive manufacturing to create these porous molds, these scaffolds, and then these scaffolds are seeded with cells, and the molds will give shape to the cells. The cells will grow, and during this growing mechanism of the cells, the initial mold will disappear. So by the end, we have a new tissue. So we can pre-culture the structure in a bioreactor before implanting the structure into the body, or we can print, seed it with cells, and implant directly into the body. So this is one strategy that we are focusing. The other one is to use, again, additive manufacturing, but to print bio-ink, so a different type of ink. So in this case, our bio-ink is based on an hydrogel, so a soft polymer with a high content of water containing cells. And we can do the same, so we can print these constructs using this bio-ink. But the beauty of this approach is that we can print these bio-inks directly into the body. And I'm going to show you one example of this strategy. Of course, that this is highly personalized because the biomolds are designed for a specific person, for a specific problem, and we can use cells from that person. So highly personalized approach. So in terms of the scaffolds, we are using a wide range of materials, and we are also using multiple technologies, some powder bed fusion, but mainly extrusion. We are also combining extrusion and electrospinning, developing hybrid systems, and we are investigating these structures both in vitro and in vivo, and we are also developing several strategies to modify the surface properties of these structures to allow a better affinity with the surrounding tissues, and also to accelerate the attachment and growth of cells. We are running several projects, but let me present one project that we started 3 years ago. We are finalizing the project. We are now starting the preclinical tests. So I have good friends in Turkey, and I visited Turkey during a critical period. So we had this war in Syria, and Turkey was receiving lots of refugees, and the majority of these refugees were suffering from health problems, and we realized that a large number of the Syrian refugees in Syria, they presented very large bone problems. We are talking about, in some cases, defects of 20 centimeters of size. And the only solution for the clinicians there was amputation. And you can imagine the impact of this in this person. So first of all, from a religious perspective, this was quite problematic, because it means that part of the body was removed. Strong impact in terms of the families. So I was very impressed with this problem. And then we decided, together with them and several clinicians, to propose a project to EPSRC, the Engineering and Physical Science Research Council in the UK, to develop what we call it as bone bricks. So small structures with a composition similar to bone, easy to assemble, allowing the clinician to, by assembling these elements, to create a synthetic bone, easy to put in the patient, filling the gap. And that's why we call it as bone bricks, so small elements to create a new bone. So we spent the first years developing everything to make the life of clinicians easier, because they don't know nothing about 3D printing. They don't have time to create these structures. So the only thing that they need is to click the button and to produce whatever they need. So we develop a couple of software tools. allowing to create these modular structures based on medical imaging and also software tools to automatically generate the path planning and the printing conditions, allowing the surgeon to click the button, print the structures, have the structures, and use them. These are examples of some anatomically designed bone bricks with a gradient of pores designed to improve mechanical properties, but also to increase the bone in growth. And as I mentioned, we characterize these structures in the lab, including biological studies, and we are now running preclinical studies using ships. We expect to finalize all these preclinical studies by October or November. In terms of surface modification, as I mentioned, we are developing several strategies. One is represented here, so we use an acetone vapor annealing strategy to induce some porosity on the scaffolds, and then we dop the scaffolds with dopamine to improve their biological properties. Another strategy is basically to coat the scaffolds with nanoparticles of silica, again improving the mechanical properties, creating a very rough but controlled surface which increases cell attachment and proliferation. Using 3D printing and a combination of materials, we're also able to create structures mimicking the real structure of bone in this case. And again, we published some papers last year showing this. So we developed a methodology using polymers and ceramics to create a structure similar to bone. So during the printing process, we observed that the hydroxyapatite mixed with our polymer was aligned according to the printing direction, so similar to the hydroxyapatite crystals in bone, surrounded by a polymeric matrix. And we mix also we add also into the mixture multi-wall carbon nanotubes, which again were highly aligned according to the printing direction, mimicking the structure of collagen in bone. So it was possible to create a biomimetic structure using this material composition and additive manufacturing. We are also combining techniques. So in terms of extrusion, it is important to create structures with large pores to allow fluids to flow, to supply oxygen and nutrients to the cells there. But very large pores create a problem in terms of cell growth. So we decided to combine electrospinning and extrusion. And again, we published a paper last year about this. So we use a rotating drum, and by adjusting the electrospinning properties, it was possible to create a dual construct with very aligned nanoscale fibers, promoting cell growth and controlling also the orientation of cells in our structures. We are exploring other material combinations. So one is focusing on electroactive scaffolds and piezoelectric scaffolds. And the idea is to again mimic the structure of bone. So bone is a piezoelectric material, but it has also a reverse piezoelectric effect. So this means that under loads or under stress, bone generates some microcurrent, and this microcurrent has a positive impact on the tissue. So the idea is to do the same. And we are doing this using graphene. Sorry for these images because this shows some animal tests. So we tested these electroactive scaffolds in rats, and we observe a much better results in terms of bone regeneration using this approach. Finally, in terms of healthcare, I mentioned that we are also developing strategies to print directly into the body. This is an example of one of our projects. So this is related to print skin. From a mechanical point of view, this is a simple system. So basically, the system comprises a scanning device to scan the body of the patient, determining damaged areas and the extension of these damaged areas. And then we use this data through a reverse engineering process to control a printing machine. Our printing machine comprises two printing heads, two different materials containing different cells from the patient, and then we print these different materials, creating a synthetic skin. We spent lots of time. We spent 3 years developing a proper bio-ink. We use pectin and we use a dual cross-linking approach. So basically, we pre-cross-link our pectin through ionic cross-linking to increase viscosity, facilitating the printing process. And after the printing, we irradiate to complete the polymerization. So we were able also to tune our bio-ink. We ran a couple of tests showing that cells were able to survive, and these results are from 14 days post-printing. So cells were live and they were creating their own matrix, so producing, for example, collagen and other proteins. And then we develop a more complex structure. So in this case, we print 2 layers of material, again containing different cells. We induce a stratification process to create the dermal and the epidermal layer. And we are very, very happy because when we compare our artificial skin, and this is our artificial skin with the human skin, it is possible to see how similar are those structures. We are trying to make the structure more complex, and I have now 2 PhD students using this approach to study melanoma, to study skin cancer problems. One recent area in my group is to use additive manufacturing for agricultural applications. So this is a project being funded by Bill and the Melinda Gates Foundation. And basically what we are doing is to replicate the structure of a leaf. It's a difficult work because it's not only a question to replicate the structure; it's also to replicate the function. And when you look to an optical image of a leaf, it is possible to observe these holes, a kind of holes. These are called stomata, and they open and close depending on the environmental conditions. And this is the mechanism through which the fungus infect the plant. So we decided to focus on a pathogen called yellow rust, which is critical in Middle East and North Africa. And what we are doing, and we successfully mimic the structure of leaf, but what we are doing now is to use smart materials for the first layer to be able to replicate this open and close mechanism of the stomata. 2 years ago, BBC broadcasted a program focusing on advanced technologies for agricultural applications, and they spent 1 minute or so presenting our project. So better than images, let me use this very short piece of that program about our project.
São 12 horas. It enters a sensor biologically engineered to mimic the crop. Like a kind of fire alarm, the sensor sets off an early alert. They can all be linked up, warning other farmers weeks before any damage is visible. And they can be 3D printed. These.
Yeah, and finally, and this will be my last example, is something that we are starting, and it's about the use of additive manufacturing for textile applications. So again, there are few examples, proof of concept related to the use of additive manufacturing in the textile sector. So additive is being used by designers to create clothes. There is a company in Italy using additive manufacturing to print ties. Simple examples related to buttons. But when we look to these examples, first of all, in most cases, the clothes are quite rigid. The materials are not sustainable, and it is not possible for the users to create their own products. And due to that, we decided in the UK to create a new center, which is the Textile Circularity Economy Centre, where the idea is to explore more sustainable materials and new technologies to create, first of all, more sustainable textile products, and secondly, to allow users to be designers also of their own products. So the program is quite complex. In Manchester, we are responsible for the fabrication part. We are using additive manufacturing, but also weaving technologies. The plan is to develop an hybrid system. And basically the aim is to change the way textiles are made, change the way textiles are designed, and change the way users are collaborating with designers in the environment of textiles. We are now focusing on the use of additive manufacturing to print textile products using sustainable materials. And one partner of the consortium is the University of York, and they are producing bacterial cellulose. And basically, we are developing a proper strategy to print that bacterial cellulose, creating a textile product. We are also focusing on smart materials, trying to develop self-cleaning textile products, or using sustainable inks, allowing to create textile products that change their color depending on the environmental conditions, or also using recyclable materials like PETG, which is a shape-changing material, to create also shape-changing clothes. In terms of bacterial cellulose, we are investigating three main approaches. So one, which is the simplest way, is mixing the bacterial cellulose with another polymer, which must be a biodegradable polymer, using a normal extrusion mechanism. The other two approaches are based on the development of a bacterial cellulose ink. And then there are two options. One is to print the ink in a coagulation medium to create the final structure, or to print the cellulose ink in a solvent, for a densification mechanism, so to consolidate the structure, and then apply radiation, UV radiation, to complete the cross-linking process in order to obtain the final structure. We start with the first approach, so we start using extrusion based machines to extrude the bacterial cellulose together with PLA and PCL. Despite the good properties of cellulose, such as the shear thinning behavior, which makes easier the printing process, it was not possible to incorporate again more than 30-35% of bacterial cellulose in our structures. So that's why we are now focusing on the ink approach. But some of the structures, the preliminary structures that we produced. The goal here is, or our final goal here, is to develop two integrated platforms, allowing anyone to be able to design and create their own textile products. One platform is related to, it's a digital platform. So basically, anyone using, for example, a mobile phone will be able to create an avatar in this digital platform. And then that person can use our material database to start creating their textile product. The digital platform will allow also the user, which is also a designer, to simulate the behavior of the textile product, so stretching, for example. The second platform is a manufacturing platform, which comprises a physical mannequin, which will be configured depending on the avatar created in the digital platform, and a robotic system integrating additive manufacturing, electrospinning, and weaving technologies to create the final product. So this is our aim, and we hope to have something in operation in 3 years' time. Of course, that we are quite interested in exploring more the use of additive manufacturing for the textile and apparel production, because similar to what's happened to other industrial sectors, additive manufacturing will allow to create a totally new textile ecosystem, allowing to develop new business models. Mass personalization is a key aspect, bespoke design, but again, more localized manufacturing, disrupting the supply chain. So because of that, we want to receive more contributions for other colleagues outside the Textile Circularity Centre, and we are launching a special issue entitled Textiles 4.0 Advanced Materials and Processing Technologies. So if you are working in this area, if you are interested in this area, please feel free to contribute. Final notes, additive manufacturing, as I mentioned, and hope to be able to demonstrate, and of course you know because you are working also in the area, allow us to create totally new products. But the way a product is designed for casting or for milling is totally different from the way we design a product for additive manufacturing. So realizing this, again, a group of universities in the UK decided to propose to EPSRC the establishment of a network focusing on design for additive manufacturing, and within this network, we are focusing on teaching. We are focusing on different applications, on standards, on the information flow, on new materials and new design tools and methods. The network is organizing regularly seminars covering these multiple areas, and all the seminars are open to all persons interested in the field. Finally, two slides. One to mention some new opportunities or emerging areas related to additive manufacturing and advanced materials, and a final slide about challenges. A significant opportunity, I believe, is related to the use of smart materials to produce smart structures. So structures that can change their properties depending on changes on temperature, humidity, current in the environment, and the range of potential applications is quite significant. The other one is related to the fabrication of functional graded structures, allowing to better tailor the properties of the structure by changing the composition of the materials that we are printing. And this is only possible through additive manufacturing. Finally, an emerging area is related to multi-material printing, allowing to create multi-material parts. And a relevant example is related to printing hydraulics, where we need to mix solid and liquid materials. And also electronic printing is another emerging area. But of course, there are challenges, as a research community, we need to address these challenges. The first one is related to the models that we have to predict and to optimize additive manufacturing, or to predict the properties of the final products. We need to have what we call it as better prescriptive modeling tools. Tools that will allow us to predict the behavior of parts being printed by using totally new materials that were not tried before, and that we don't know the final response. So this is critical also to minimize the extensive experimental work required. Measurement and the inspection is another area. Of course, that CT is a key technology, and there are lots of groups developing strategies related to the use of CT, but uncertainty estimation and the calibration of the system is still a problem. And finally, we are not paying too much attention to this, is the health and safety issues related to additive manufacturing. Even a small printer printing ABS offers some health problems due to the vapors released. So we need to pay more attention about the health and safety issues related to additive manufacturing, and we need to have, again, better standards related to the materials to improve the health conditions related to the use of additive manufacturing. So a couple of challenges that we have in front of us in the field of additive manufacturing. I think that I talked too much. I'm very sorry for that, and I finish by again say thank you very much. It was a great pleasure to be part of this seminar. Thank you very much.
Thank you very much, Prof Paulo Bartolo. Now the session is open for questions. You can raise your hand and start asking questions. Vidya Dhop, Dr. Manish Arora.
Hi, Professor Paulo. Good to hear you talk again, and was a pleasure to hear wide variety of things you're doing in Manchester. I had a question about the 3D printing and construction. You talked about building structures where only certain load factors are accounted for. And I was wondering, as I was thinking about it, these things will have lifetime of over 20 years or maybe even longer in some cases. And often we assume that the structure will be robust to changes. You might change its use to some extent. Now that you've designed it so specifically, how does it survive in its post production period, as in its use case? Will people have to have simulation tool again available with them, or how do we kind of manage that?
Yeah, no, Manish, that is, it is again a great pleasure to listen to you, and I hope to be able to visit you again soon. No, that is a very important question. But it's not only related to construction. Even, for example, using metallic printing machines for aerospace applications. Yeah. So we are trying to convince of companies in Manchester to work with us, and one institute that we have in Manchester related to health and safety, to investigate the long-term performance of different 3D printed parts, not only for construction. In fact, we are not in construction. We are more focusing on aeronautics and aerospace applications because, again, we don't know. We need to know long-term performance of those of 3D printed parts. Yeah, it's a very important subject.
Sure, thank you for addressing that.
Thank you very much. Ms. Vidya Dopati.
Yes, thank you for the wonderful session. I'm not strictly from a mechanical background, I'm more from a computer science background. So I wanted to ask a very basic question, which is related to how you said that additive manufacturing is very useful in mass personalization. And as I understand it, the limitations with traditional manufacturing in mass personalization would be the molds which are used. So is it correct to assume that because additive manufacturing doesn't really have molds, and since there are designs, that is why it helps in mass personalization?
Yeah. So that is one of the main reasons. So we don't need to have tools to produce parts. So there is a famous graph showing the point from which conventional manufacturing is the ideal technology, and behind that point, additive manufacturing is the ideal technology. And most people have been focused on mass customization, so small series. I believe that the biggest opportunity of additive manufacturing is for mass personalization. So in some sense, is to return to the beginning. So if you think about the evolution of manufacturing, long time ago, we started as a craft production, using very skilled persons to create individualized products. The problem was the price and of course the time to produce those parts. I think that the next industrial revolution will be to return to this craft manufacturing, but in an automatized way. Yeah.
Yeah, that's very insightful. Thank you.
May I ask a question if I am permitted, Professor? Professor Paulo, may I ask a question?
Please.
Yeah, thank you. You spoke about the organ or biological printing. Was it able to achieve vascular printing, or where is the stage with the bioprinting part of creative manufacturing?
Yeah. So in one of the slides, the slides where we performed the animal studies, it is possible to observe a mechanism that we call it as angiogenesis, so which is related to the formation of the prevascular system. So yes, so we have different strategies to do that. Some strategies are based, for example, on the incorporation of growth factors. Other strategies are simply because these materials, and we realize that with these electroactive scaffolds. So basically, our electroactive scaffolds are produced using a standard polymer, which is PCl, with graphene or multi-wall carbon nanotubes. And in both cases, we observe that after a certain period of time, the result of the use of these scaffolds with the application of electrical stimulation not only induce the formation of new bone, but induce also the formation of the vascular tooth system. Of course, that the experimental work was limited, so we ran these tests, I believe, during 3 months or so. So we need to extend the preclinical trials to know better what's happening in terms of long-term use of these scaffolds. But yes. In all the experimental work that we conducted, we observed the formation of the vascular tooth system.
Yeah, thank you. And in your opinion, how much time do you think will take before a personalized glomerulus is produced using 3D printing or additive manufacturing?
Bye-bye.
Yeah, that is Rina, the most difficult question. So. As a researcher, we are always thinking, okay, the work is going well. We'll be able to launch something into the market very soon. But yeah, regulations are quite strict in Europe, and yeah. So we believe, especially related to the bone bricks. What we have in mind is after this first phase and after the first preclinical trials with chips, our plan is to submit another proposal to, first of all, to repeat the preclinical trials with bigger animals, and then to do some human trials. But again, this will take time, and we are talking. By the way, we are talking about simple structures like bone. To give you an idea about how complex is the field, in 2006, I was invited to attend a meeting in Washington, organized by the National Science Foundation. About tissue engineering, and but by the end of the meeting, the person from NSF, he was very pragmatic, asked, okay, we need to provide a report by the end, and we need to put targets. So when do you expect to have a successful organ 3D printed? And on that time, people mentioned, okay, by 2020, we'll be able to have a liver. I think that 5 years later, the same group decided to postpone the date till 2025. And by 2025, that will not be possible. Because for complex organs, and liver is a complex organ, we need to have better materials, and we need to have better machines. We don't have yet machines that allow us to replicate the complex hierarchy of organs. So that's why in our case, we decided to focus on simple structures for bone, Bone is relatively simple structures for skin, and that's it.
Thank you very much, Professor. Professor Reena Maiti.
Yeah, thank you, Professor, for your presentation. I'm having a little question on bone graft, means scaffolding for the bone. So what I know that for different bone, the structure is very different, as well as surface is different, geometry is different, and not only geometry is different, it is not isotropic throughout the geometry. Now the thing is also how the bone growth is happening. It is basically because of how the stress reduction is. There is the osteoblast, osteoclast, basically the changeover of that. So now that is basically depends on, even it is not very sure which parameter actually stimulating them. If we don't understand the process itself, physiological process, then how we are actually, how successful we are to simulate that kind of environment. And then if it is done, how much it is effective in performance or in structural stability or bearing the load that way. So, and also it has to be fine-tuned, or it is to match with the outer surface. Whatever the portion has been cut, it has to be matched with the other surface. How it is happening? Can you please talk about it? Yeah, please. Thank you.
No, again, very interesting question. I will start by your final point. So because we are only using combinations of biopolymers and bioceramics, we are not able to create structures with properties suitable for load-bearing applications. So, in the case of the Bone Bricks project, for example, and we are talking about a very large defect, we still need to use metallic plates, and the metallic plates will support most of the loads. We published few papers where, with the addition of graphene and multi-wall carbon nanotubes and a specific design of the scaffolds, we approach the properties of bone. But yeah, so we decided not to focus on the mechanical properties because that will be difficult to achieve. We decided that we will still use metallic plates, and in that case, our goal is to redesign the metallic plates to eliminate the stress shielding problem. Now, in terms of designing the scaffolds, mimicking the environment of the tissue, we are close to do that because so we have a large number of students focusing on different combinations of materials, other students focusing on the design of the architectures, other students focusing on the development of new machines to create much more complex structures. And you mentioned a good point, also the surface characteristics, and we are able to tailor and to decorate our scaffolds with different materials to mimic the environment of bone. Of course, that we are doing this step by step. So everything related to new bone formation, so cell growth, differentiation, vascularization, we have been investigating. But for example, and I don't believe that other groups are doing that. We are starting to do it, which is focusing on innervation. We have a nervous system in a bone, and people don't pay attention to it. So again, because our aim is to mimic the complexity of bone, we are starting now a new project where one student is trying to design a structure to promote innervation. So the idea is block by block be able to replicate the bone environment.
Yeah, as because there is vascularization, there are specific enzyme kinetics, there are interconnectivity. All these things are important. Otherwise, the structure is will be very difficult to.
Yeah, but that's why we are developing our own machines. So for example, for vascularization in bone, one potential approach, and we have done that, is to combine a normal extrusion machine and a printing machine to print a more soft material with a sacrificial material inside, and then after the fabrication we remove that sacrificial material and do a perfusion process. So that is not of course that we need to develop better structures, even considering that, but we have done a lot. That is not our major focus now.
Okay, thank you.
Thank you very much, Professor Lirena Maiti, and also thank you very much, Professor Paulo Bartolo. So I think with this, the session comfortably and at exactly 5 p.m. we may declare it end with due permission from Professor Paulo Bartolo. Professor, may I end the session?
Yes, let me say only again, thank you very much. Thank you for listening to me. Thank you for your questions. You have my email. If not, Professor Amresh can provide my email. Feel free to contact me, and I hope to be able to visit you soon. And thank you again, Professor Amresh.
Thank you.
Thank you. It was a wonderful session, and very happy that the professors are all here and very keenly listening to you. It shows how important this session is. And I say one specific request from you. We would like to publish this on YouTube as part of the 75 years of Indian independence celebrations. May I seek your permission also for that, so that this session can be published on YouTube.
Yes, of course.
Thank you very much. Thank you. The session ends now. Thank you.
Thank you, Professor Paulo.